In this lesson, we're going to take a look at Lewis structures. Now, we've looked at electron dot diagrams, which are also called Lewis dot diagrams, and basically these are going to help us figure out what molecules look like. They give us cartoons of molecules. So first, a quick review of Lewis symbols. Remember, these show us the valence electrons around a symbol, and when we're drawing these, we don't give any side of an atom two dots or two electrons until every side has at least one, and we only put up to two dots per side. So if we pick argon, argon is a noble gas. It's a group 8A element, so it has 8 valence electrons. So it doesn't really matter, we can put all those around. But if we pick something like oxygen, oxygen is a group 6A element. It has 6 valence electrons. So when we go around it, we put one on each side, and then 5 and 6. And the reason we do it that way is because it turns out unpaired electrons usually are the ones that form bonds. Now we'll get into some fun Lewis structures where we change that up a little bit, but for the most part, if you look at this, you can look at oxygen and say, okay, it's got 2 open spots and 2 lone pairs of electrons. Well, the open spots will form bonds, the pairs generally do not. Okay, so we draw Lewis symbols to help us figure out how bonding is going to occur. We can also use Lewis symbols with ions, which is not a covalent bond. So when we do ions, we show the charge and the valence electrons of the ion. Now this is actually something like sodium, Na. Here's the Lewis symbol for sodium. It's got 1 valence electron. Here's the Lewis symbol for the sodium ion. It's a sodium plus because it gave away that electron. Chlorine, of course, it's got 7 valence electrons. The Lewis symbol of the chlorine ion is Cl minus with all 8 valence electrons. So when you have Lewis symbols of ions, they should either have no valence electrons or 8 valence electrons. And I picked things that only had plus or minus 1 charge, but if we did aluminum, which has 3 valence electrons, then its Lewis structure is Al3+. And if we did nitrogen that has 5 valence electrons, then its Lewis structure with 8 has a 3- charge. So we use the number to denote how much charge. Now you can also use a Lewis symbol to kind of symbolize or visualize an ionic compound, but we don't actually draw structures for them. So if we look at this sodium and chlorine, we could actually have Na plus and then Cl 1, 2, 3, 4, 5, 6, 7, 8 minus, and that would be our compound for sodium chloride, but it's a heck of a lot easier just go sodium chloride. What we do though is we can draw Lewis structures of molecules. Now remember, a molecule is a group of covalently bonded atoms. So it shows how these atoms actually bond and what they're doing when we form molecules. And a Lewis structure only exists for molecules, not for ions, because in an ion you have a crystal, and the crystal structure is repeating, and that pattern can just keep getting bigger and bigger and bigger. Unlike a molecule eventually ends. Now, a couple things to keep in mind with the Lewis structure is that we're going to follow the octet rule. And there's a few exceptions to that, but the major thing is atoms generally like to have 8 valence electrons. And then we draw bonds as lines to show where atoms are forming bonds. And we know that we can actually have bonds as single, double, or triples, and we'll get more into that in just a second. And so a bond involves a pair of electrons, which means a single bond is 2 electrons, a double bond is 4 electrons, and a triple bond is 6 electrons. And when you're counting these up to make sure you're following the octet rule, you need to pay attention. Every line is 2 electrons. Then there's occasionally these diatomic molecules that are only found in pairs if they're not in a compound. And those are Brinkelhoff, which is bromine, Br2, iodine, I2, nitrogen, N2, chlorine, Cl2, hydrogen, H2, oxygen, O2, and fluorine, F2. So these are diatomic molecules. If we don't see them in compounds, then they have to be paired up in a chemical reaction or when we write them. So when somebody says oxygen, they mean O2, oxygen gas. So what does Br2 mean? Well, it means if we take a bromine atom, and we're going to draw the Lewis diagram for it, it's got 7 valence electrons. And if we have another bromine atom, then it also has 7 valence electrons. Now both of these things would actually like to have 8. Neither one of them wants to give away an electron. So what happens is these 2 electrons are actually shared between the 2 bromine atoms. And so we end up with bromine sharing 1 pair of electrons between them. And that's what I mean when I say bonds are drawn as lines. That dash between the 2 bromines tells me, oh, they're sharing those 2 electrons. So there's bromine with the with one single bond between them. Okay, and I said we got to follow the octet rule. Well, here's 2 electrons, here's 2 electrons, here's 2 electrons, and here's 2 electrons. So this bromine sees 2, 4, 6, 8 valence electrons, which is a stable number. This bromine, 2, 4, 6, 8. You'll notice the bonded electrons get to count for both because they're shared. They both atoms actually share those electrons, so they count for both. So what about something like nitrogen? Nitrogen has 5 valence electrons. If I look at that, I see 3 open spots on a nitrogen, and so I'm going to draw this Lewis structure a little bit different because there's 1 bond, 2 bonds, and 3 bonds. And this is the sketch to help us actually come up with the actual Lewis structure, which looks like this: 2 nitrogens, and this is a triple bond. Now again, we got to follow the octet rule. So there's 1 pair of shared electrons, which is 2. There's another pair, which is 2. There's another pair, which is 2, so I have 2, 4, 6, and then my lone pair, which is not shared, that's 8. So this is a triple bond which has 6 total electrons in it, and then our lone pair that's not bonded. So both of these follow the octet rule. Both have 8 valence electrons, even though the middle 6 are shared. Oxygen does a similar thing. Remember, oxygen has 6 valence electrons, and when oxygen forms a bond with an oxygen atom, it shares this pair and it shares this pair, which gets us the Lewis structure, O double bond O. And now we followed the octet rule: 2, 4, 6, 8, 2, 4, 6, 8. So these are simple Lewis structures for the diatomic molecules. We're going to take a look at some more complicated ones and what rules we follow when we're drawing Lewis structures. Use the symbols. Use the Lewis symbols to help you. The structure is usually pretty easy to get from that. Hydrogen is sort of the exception, except it's still easy to get from the symbol, right? Hydrogen only has 1 valence electron, but it's only got to fill the first energy level. Remember, 1s2, and then we go to the next energy level. So if we get 2, it'd be happy. So those 2 electrons share, and so hydrogen is like that. And we can clearly see that because each has 1 single electron that's free to bond. Okay? Water is H2O. What does this look like? Well, if we draw the Lewis structure for, or the Lewis diagram for hydrogen, it's that. The Lewis structure for oxygen is this, and we can see, all right, well, hydrogen would like to have 2, it can share there, and water would like to have 2, and so it can share with 2 hydrogens, and we get this thing where we can draw HOH, and there's the Lewis structure for water. Okay, we got that because we could clearly see these lone electrons, single electrons, like to form bonds, pairs, not so much. Carbon dioxide, this one's a little bit tricky, but not too bad. If you start with carbon, it's got 1, 2, 3, 4 valence electrons. Now remember, carbon dioxide is CO2, so we need 2 oxygen atoms. Well, if I start with an oxygen here, that can bond and that can bond, and then I have 2 left, which means another oxygen can bond over here, so we got a bond and a bond, and so we turn this into a Lewis structure by writing oxygen, double bond carbon, double bond oxygen, and then fill in your lone pairs. You'll notice carbon does not have any lone pairs, but it still has 8 valence electrons, 2, 4, 6, 8. Oxygen still has 8, 2, 4, 6, 8. So everything follows the octet rule. We're golden. So if they're simple structures, that's pretty straightforward. But if they get a little bit more complex, then there's some rules to follow. And we're going to run through a few of these. They're not bad, but sometimes we get a little confused. So here are step-by-step directions. Some directions are better than others. Sometimes stuff works out better than others. But first thing is we're going to figure out how many total valence electrons do we need. So if we're thinking something like water, H2O, we know that each atom, each hydrogen atom contributes 1, so we have 2 times 1, plus the oxygen atom, which contributes 6, so we know we have a total of 8 electrons to place. If we had something that was charged, like a cation, like a polyatomic ion, like carbonate or ammonium, then we would have to add electrons for each negative or subtract electrons for each positive. We'll look at an example like that later. Then it says, draw a skeleton structure of the molecular ion, arranging the atoms around a central atom. So that means like a central atom is the least electronegative, but hydrogen can never be a central atom because it can only make 1 bond, and fluorine is never a central atom because, well, it's the most electronegative. So in water example, this is my central atom, so I'm going to draw a skeleton by just drawing single bonds like that, and then it says distribute the remaining electrons as lone pairs on the terminal atoms except hydrogen, because hydrogen can't have any more electrons, so that means I'm going to distribute lone pairs, and I've got 2, 4, 6, 8, and that's water. It's pretty easy. Place all the remaining electrons around the central atom if we can't do terminals, and then rearrange anything on the outside to give more bonds if we can. So we're going to have to look at that one in a minute. But those are the rules. Really, if you practice this a few times, you won't even think about the rules. You'll just be counting to 8. That's the major rule with Lewis structures, is count to 8. So let's take a look at an example that makes us use the rules, because these are a little bit more complex than just those simple structures we were looking at before. So this says NH4+. So the first thing I'm going to do is count up how many valence electrons I need. Nitrogen is a group 5 element. It has 1, 2, 3, 4, 5 valence electrons. Hydrogen is a group 1, right? It's got 1 valence electron, and I have 4 of these, so 4 times 1. And then this says plus, which actually means I have to eliminate an electron. So if I have a positive, I have to actually subtract 1. So I have 5 plus 4 minus 1, which equals a total of 8 valence electrons that I have to place. Next rule says, let's start with the least electronegative, and hydrogen can never be a central atom. So I take nitrogen, and it says draw a skeleton structure to each terminal atom. So here's hydrogen, 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 hydrogen. Okay, and then make sure I've met all my valence electrons. 2, 4, 6, 8. Oh, I totally did. Then I'm going to put this thing in a bracket and go plus, because it's actually a positive ion that's covalently bonded together. So my central atom is obeying the octet rule. Hydrogen's happy because it's got its 2 valence electrons. I've placed all 8 valence electrons, so this one wasn't so bad. If we'd have tried to do that with a skeleton structure, we could see how this would work, but then if we try to place a hydrogen here, we get confused because we usually think that a pair doesn't bond. But remember, that one actually got kicked off, and then that pair is actually shared. So we have 4 single bonds holding this thing together. Another example, a little bit more complicated, is carbon monoxide. So carbon monoxide is not carbon dioxide. There's only 1 oxygen here, and this one's fairly toxic. So carbon has 4 valence electrons, and oxygen has 6 valence electrons. This is 10 valence electrons. Okay, so there's not really a central atom here because these are just 2. So I can take carbon, and I'm going to draw a skeleton by bonding it to oxygen, and then I'm going to go ahead and place the rest of my valence electrons. Okay, I have 2, I need 8 more. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, well, that gives me a total of 10, but nothing here is very happy because nothing obeys the octet rule. And the way I get around that is I say, oh, well, we can actually just go ahead and bond, right? A pair of electrons, if each one of these donates to a bond, then I can put in this electron bond. So this thing kicks, we're going to go ahead and do it like that. This oxygen kicked in a pair of electrons, which now if you look, carbon has 2, 4, 6, 8, but oxygen only has 6. So carbon will say, well, hey, I'll share these 2 electrons over 2, and so now instead of having a single bond or a double bond, now I have a triple bond, and I have carbon, triple bond oxygen. Okay? I've placed all 10 of my valence electrons, 2, 4, 6, 8, 10, and everything obeys the octet rule, 2, 4, 6, 8, 2, 4, 6, 8. Here's another one that involves an ion. So I have carbon, which is 4, oxygen, 3 oxygens, which each have 6, and then 2 negative, which means plus 2 more. So I have 18 plus 2 is 20, so I have to place 24 valence electrons to get this thing to work. Carbon is going to be my central atom because it's the least electronegative. So I'm going to start with carbon. I'm going to go oxygen, oxygen, oxygen. And now I'm going to start placing all my remaining electrons, right? Here's 2, 4, 6. That means I need 18 more, so I can put 2, 4, 2, 4, 2, 4. I'm not going to place any on carbon yet because I place all my electrons on terminal atoms before I place on my central atom. So I have 2, 4, 6, 8, 10, 12, 14, 16, 18. And I need 24, so I'm going to go ahead and 2, 4, 6, 8. Now I've placed all my electrons, right? I've got essentially 8 on every carbon atom when you count the one in the bond, which is 24, but carbon's not obeying the octet rule, which is okay because I can pick any oxygen and I can say, let's slide these 2 electrons into a bond. If I do that, then I didn't lose any electrons from this oxygen atom, but I gained 2 electrons to that carbon. So now I have a double bond to this carbon and oxygen. Okay, well, why did I pick that oxygen? Well, I just randomly picked it. It could have easily have been O double bond carbon, oxygen, oxygen, fill in your electrons like this, and this would be a different atom or a different structure. So there's actually 3 resonant structures, we call them, that don't exist simultaneously, like shifting from one to the other. Instead, it's some hybridization between all of them, and sometimes you'll see this drawn as a dashed line between the oxygens to try to represent that there's some hybridization going on, but there are actually 8 valence electrons on everything. Okay, so this is the Lewis structure for it, but you can draw 2 other ones, right? We could put the double bond here, or we could put the double bond here, and those are called resonant structures. Okay, all right. Now there are a couple things that disobey the octet rule. Oh gosh, that seems scary, but it's not bad. Boron is a big one because it's electron deficient. Boron is 1s2, 2s2, 2p1, okay? Which means it could actually fill that 1p orbital with 1 extra electron, and that would mean that it might be happy if it's only got 6 valence electrons instead of all 8. So if you look at boron, its electron dot diagram looks like this. It's got 3 valence electrons. Well, it's content in BF3, or boron trifluoride. If we fill in that fluorine like this, it'll share here, and then it can also share to another fluorine and another fluorine. Okay? And you'll notice that gives boron only 6 valence electrons, but it doesn't actually have any over here, so this is a stable, okay configuration. It does not obey the octet rule, but boron's an exception. Then there's things that expand their octets, which means they disobey the octet rule in the other direction. They actually take more than what we'd think would normally be allowed. So elements in period 3 and beyond have the d orbital that's empty, right? Because remember, it goes 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. That third energy level has a d orbital that isn't full yet, even though we start over in the 4th energy level. So that d orbital is actually available for the bonds, or the electrons, to move into as long as we're in the 3rd period and beyond. And that means occasionally we'll get central atoms that have more than 8 valence electrons. So sulfur hexafluoride is a classic example. Hexa means 6, so I have SF6. Well, fluorine has to be a terminal atom. It's the most electronegative, which means I'm going to have sulfur, 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 making 6 bonds, F, 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 F. And now I can fill in all my valence electrons, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Now, if I want to make sure I'm following the rules, the octet rule is broke, because you'll see sulfur's actually got 2, 4, 6, 2, 4, 6, 8, 10, 12 valence electrons in its octet, but that's okay. It's got 12 in its octet because its octet is expanded into D, so it's not really an octet anymore. But sulfur has 6 valence electrons, fluorine has 7, and I have 6 of those, so that's 48 valence electrons to place. Well, every fluorine has 8 when we include the bond. There's 6 fluorines, so there's all my 48 electrons. So it works. Xenon tetrafluoride is a little bit different. Xenon is a noble gas, and you're thinking noble gases don't react. Well, that's generally true, but you can make them do funny things under funny circumstances. So xenon does have empty d orbitals, which means it can actually form some bonds. So xenon has 8 valence electrons, and fluorine has 7. I'm going to start by drawing my skeleton structure. So here's xenon, and it says tetrafluoride, so that's 4 fluorines. So I'm going to draw my skeleton, and then I'm going to start placing electrons on my terminal atoms. And xenon has 8, fluorine has 7, and I have 4 of them. So 4 times 7 is 28. So I should have 36 total electrons when I'm done here? Well, if I put 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. If I put all those electrons around, then I have 8 on every fluorine, which is a total of 32, and I still need 4 more electrons, and they go right here on my central atom. So there's my 4 more electrons in pairs here. And again, I have xenon that's actually got an expanded octet, a hypervalent 2, 4, 6, 8, 10, 12 valence electrons around it. But that's okay because it's got those empty d orbitals. So third row and beyond, things like that happen.